welcome everyone to a very much requested deep dive session. It's our Border Gateway Protocol, our BGP Deep Dive. We've done a lot of these deep dive sessions over the past couple of years or so. We've done them on OSPF and EIGRP and Spanning Tree Protocol. And I think one or two other topics. Wireless. We did a deep dive on wireless not long ago, but this has been requested a lot. So I thought it's time we finally get around to it. Let's do a deep dive into BGP. And to be honest, one reason that I was a bit hesitant initially is that BGP is so deep, this could go on for many, many hours. So I thought, all right, let's do a deep dive, but let's constrain the topics to something around the areas of certification. So we're mainly going to be focused on ENARSI and ENCOR BGP exam topics. I'll get a little bit beyond that for those CCIA candidates out there, but there is just so much to it. And there's a lot of, I call it FUD, fear, uncertainty, and doubt around BGP. I remember when I was going after my very first CCIA certification, one of the biggest topics that I was so concerned with was BGP. And I printed out the configuration guide from Cisco. I think it was like 90 pages long. I read that thing from front to back. There is so much you can do with BGP, and we're going to get way deep into the weeds today. But if you've not worked with BGP, no worries, because we're going to start with the basics and then work our way in and get deeper and deeper and deeper throughout these couple of hours or so that we're going to be spending together. But I just want to begin by saying thank you. Thank you for entrusting me with a couple of hours of your time. That's what I'm guessing. 2 to 2.5 hours is my rough guess as to how long we're going to be going through this deep dive. Here are the topics coming up today. For those of you without any experience at all, I want to set a level playing field, and we'll cover some of the basics of BGP. What are some of the characteristics that distinguish BGP from some other routing protocol? We'll talk about in theory, confederations. We'll talk about route reflectors. That's going to overcome an issue that we have with BGP neighbors, and we'll define what all that means, so no worries there. We'll talk about how two BGP-speaking routers can form neighborships with one another to exchange that route information. Spoiler alert, it's done very differently than it's done with something like OSPF or EIGRP. And then we're going to do our first configuration of the day. And there's going to be a lot of demos coming up today. The first one, I want to show you that we can take two BGP routers or two routers and make them BGP routers with 3 commands. That's it. We can make neighbors and have those neighbors exchange route information with just 3 commands. Hopefully that will give you a little bit more ease if you do have some of that fear, uncertainty, and doubt like I used to have, that this is a very learnable technology. So we're going to get it working basically, and then we're going to start adding on some features. We'll talk about how BGP makes its path selection. If it's got 3 or 4 different ways to get out to the rest of the world, which one does it use? If we're accustomed to regular routing protocols that we might use inside of our company, like EIGRP and OSPF, we might say, oh, we're just going to take a look at the metrics and we'll go with the least metric. No, not at all. It's much more convoluted than that. But after we talk about path selection, we'll talk about an older feature that you might not face in the real world, but you might face on the certification exam, and that's a rule that BGP has that's called BGP Synchronization. I'll configure that for you and show you before and after synchronization. We'll talk about summarization because BGP, that's the protocol that runs the internet. All these routers around the world making up the worldwide internet, they're using BGP in order to talk to one another. And we're going to see that they have hundreds of thousands of routes in their routing table. Instead of sending out hundreds of thousands of advertisements, maybe we want to summarize those. I'll show you live how to do that. We'll talk about how we can have neighborships formed between a couple of routers, even though they're not physically adjacent. We'll talk about the next hop self behavior inside of an autonomous system, and we'll demonstrate that. That's going to help us with some troubleshooting later, so keep your eyes open for that one. We'll talk about how peer groups can help reduce our configuration. Then we're going to get into some of the more advanced configuration, like setting up routing for both IP version 4 and IP version 6 using the address families approach. This is called, for your notes, I want to have you write down a bunch of terms today, MP, multi-protocol BGP. And normally when we talk about multi-protocol BGP, there's only two protocols, IP version 4 and IP version 6. We'll see a couple different ways of setting up BGP routing. And I want to make sure you get this in its entirety. I don't want you to come away from it because a lot of these topics are complex. I'm going to do my very best to simplify these for you. That's one of the things that we try most to do here at KW Train. Take these crazy concepts that are really, really hard to get our heads around, and simplify them. So if you stick with me to the end, I got a gift for you. If you stick with me to the end, I'm going to allow you to download for free. I'll give you a link at the end of class today of a PDF of all the slides. The slides that we're going to go through today, you'll get a PDF of those slides. You can review those. If you use something like a CML, Cisco Modeling Labs, to lab up your own scenarios, then you're going to be able to download the YAML files that you will import into CML, and all the topologies that I'm working on today, you can work with those as well inside of CML. But if you want to know what to do once you get those topologies up, I'm going to give you demo scripts of every demo we're doing today. And it's not just the steps we go through to do the configuration. This PDF that you're going to download, it's got the setup. You can literally copy and paste the setup commands from this PDF into your router configuration in CML that you've already got the topology for from the YAML files. Basically, I want to set this up so you can recreate everything we're doing today on your own to reinforce that learning. Again, that's my gift to you for staying around to the end of class today. Now, for those of you that don't know me, I saw somebody chatting in that this was their first live event with me. Those of you that don't know me, here's my super quick bio. Again, my name is Kevin Wallace. I've got a couple of CCIE certifications, one in enterprise infrastructure and one in collaboration. Got my first CCIE back in 2001. So I've reached that 20-year mark. So I'm now what they call a lifetime emeritus, which I love. I don't have to recertify, and I get to keep my CCIE for life. So I was really looking forward to the day when I got to do that. So I reached that, I guess, last August. So pretty excited about that. But I've been working with Cisco gear way before that, since 1989. I used to work with the very first Cisco router out there, the old Cisco AGS Plus router back in the late 80s, if anybody remembers that. I taught courses for Cisco Learning Partners for about 14 years. For real world experience, I was a network designer down at Walt Disney World. My family and I are huge Disney fans. You might be able to see some Disney and some Star Wars stuff in the bookshelf behind me. But I got to be one of their network designers. I got to design the network years ago that tied together the Magic Kingdom and Epcot and the studios and Animal Kingdom and some of the resorts. Big Disney fan, and it was a massive network with over 500 Cisco routers, thousands of Cisco Catalyst switches. It was just a great experience to work there. Written a bunch of books, done a bunch of videos for the folks over at Cisco Press. Got to speak live a couple of times at Cisco Live, and was honored to get their Distinguished Speaker Award each of those times. Bottom line is, folks, I love this stuff. I'm passionate about this stuff, and what I try to do, I try to create content and training that I wish I had. I would love to have had what you're about to get when I was studying for my first CCIE, and I was struggling with some of these BGP concepts. So we're going to break this into a couple of parts. We're going to have part one, and then we'll do a little Q&A break. Now, obviously, we're not going to be able to answer everybody's questions because the volume of people here. Let me do a quick check. We're on some different platforms. Yeah, right now it looks like we're at about 800 people watching us live right now. And so it's just not reasonable to try to answer everybody's questions. A big shout out to Charles Judd. He's behind the scenes right now. He's working chats, so he'll be able to answer some of those. But with 800 people, he probably won't even get to all those questions. So please let me pre-apologize if we don't answer your specific questions, but we absolutely are live. Charles is in the background handling the questions. I'll take a break midway through. I'll try to answer some questions as well. Let's dive in. To begin with, some of the basics of BGP. I mentioned earlier that BGP, the Border Gateway Protocol, that's the protocol that runs the internet. It interconnects the routers running in these internet service providers. And when I started working with BGP, it was back in late 1990s, like 97 perhaps, like 25 years ago. About 25 years ago, I started working with BGP at a university. And the reason we started using BGP is instead of just having one internet service provider that got us out to the internet, we had two. So we wanted to be able to load balance and control which traffic or which link we used going out and coming in. So we used BGP and we had peering relationships with them. And our router, I remember looking at the routing table on that router back in like 97. There were about 65,000 routes. We learned the full internet routing table, about 65,000 routes. And that just blew my mind that how many networks are there in the world? But here's a chart, and I gave you the URL if you want to keep up to date and check that from time to time. I took a screenshot of this yesterday. This shows us data from earlier in June, earlier this month. And we're over 900,000 routes in the full internet routing table, quickly approaching 1 million. And this is something you just got to know if you're working in an enterprise environment and using BGP to connect out. There's a lot to know about it. So let's talk about where it plugs in into an overall enterprise network. Here, let's say that we've got this building and that's our enterprise. For redundancy, like we did at the university, I've got a couple of paths to get out to the internet. I've got two internet service providers, ISP1 and ISP2. And there's one type of protocol that I might run within that building, within my organization. That's called an IGP. An IGP, here's a term for your notes, that's an interior gateway protocol. An IGP is an interior gateway protocol. It runs inside of what we call, another term for you, it runs inside of an autonomous system. An autonomous system is a network under a single administrative control. So the company I work for, let's say, if I work for this large enterprise, we can be assigned one autonomous system to represent our company as a whole. I'm connecting out to one ISP. They have their own autonomous system. I connect out to another ISP. They have their own autonomous system. But within my network, within my autonomous system, I'm running an IGP, an interior gateway protocol. Examples would be RIP. Please don't run RIP. That's a whole nother story. OSPF, EIGRP, ISIS, the intermediate system to intermediate system. But what if I want to talk outside of my autonomous system? We have another class of routing protocols, and that is EGP. See, everybody has their own autonomous system number now. ISP1, ISP2, my company, we've got different AS or autonomous system numbers. And it's going to be an EGP, an exterior gateway protocol that talks between autonomous systems. And currently, you'll see that I just listed one EGP, and it's called BGP, the Border Gateway Protocol. Just a bit of historical trivia for you. Can anybody tell me in the chats, and I'm looking at a couple of different chat interfaces. We've got some people joining us on YouTube, some people joining us through our site. But can anybody tell me, once upon a time, there was another exterior gateway protocol. Can you name it? And by the way, I know there's a few seconds of delay from the time I ask something and the time you hear it. It's like a 15 to 20 second delay. So I'm currently killing 15 or 20 seconds to give you time to type that in. But what is a previously existing, we don't see it anymore, exterior gateway protocol? Does anybody know it? Let's take a look at it. Let's see. Yeah. Cheryl was the first one that I saw with the correct answer. And lots of people are coming in with it now. It's EGP. That's right. There was an EGP, an exterior gateway protocol, that was named EGP. That's like having a car named Car. That wasn't very imaginative. But I remember the day when Cisco iOS supported that. I could choose between EGP or BGP. Well, that's gone. That was just kind of a historical note for you. But I want you to understand, please take a note on this. There are two flavors of BGP that we want to know about, and they behave differently. And we'll see some of those different behaviors today. One flavor of EGP is called BGP with a lowercase e and then uppercase BGP. And EGP, that's an external BGP. It runs between autonomous systems, like between our company and our different internet service providers. There's another type of BGP that can actually run inside of our own autonomous system, and it's called iBGP. We don't have to run that necessarily. If I'm just wanting to do eBGP out to my service providers, I might not want to do iBGP. I don't have to do that, but some design scenarios make that a good thing to do. I did a BGP training years ago for a very large international bank, and they used it pretty much all over the place. They used interior gateway, or interior, I should say, internal BGP inside of their banking locations. So those are two flavors of BGP, and I want to make a big note of it here. So here's the definition again for your notes, or if you stay to the end, you can just download this. And that is internal BGP that runs within an autonomous system. External BGP is going to run between autonomous systems, and they have different levels of believability. Do you remember from some of your earlier networking studies, you learned about this concept called administrative distance? Administrative distance was the believability of a routing source. Well, the believability, and lower is better, by the way. Well, eBGP that's running between our autonomous systems, it is very believable. It has an administrative distance of 20. That beats out RIP and EIGRP and OSPF and ISIS. It's very believable. But iBGP, I've got it highlighted for you on screen, not so believable. It's got an administrative distance of a whopping 200. Basically, if you have an interior gateway protocol that is carrying the same route as iBGP is carrying, you're going to listen to that interior gateway routing protocol like OSPF or EIGRP. But I did want you to be clear that there are two different flavors. Now let's run down some characteristics. Number one, we've already mentioned. It's an exterior gateway protocol. Primarily, yes, you can run it inside, but we consider it to be an exterior gateway protocol that interconnects autonomous systems. And that's what the internet is. It's this big interconnection of autonomous systems. And just like, well, not just like, but similar to OSPF and EIGRP, these BGP neighbors or these BGP routers, they can form this relationship called a neighborship. And that's going to allow them to exchange route information. Now, RIP, for example, it doesn't do that. It just sort of multicasts out, or broadcast if it's version 1, but typically it's going to multicast out, hey, here's my routing table to whoever wants to listen. OSPF and EIGRP, they're a bit more strategic about that. They send hello messages out to a multicast address saying, hey, I'd like to form a neighborship with any other OSPF or EIGRP speaking routers out there. That's not the way it works with BGP. Yes, they do form neighborships, but not by sending hello multicasts. Can you imagine trying to do that over the internet? No. We're going to statically configure the IP address of our neighbor. Then we're going to go to that neighbor, or whoever owns that neighbor is going to go to that router, and they're going to point to our IP address. So we're pointing to one another's IP address. We're not dynamically discovering one another as neighbors. That's a big distinction. And once we point to one another's IP address, we actually set up a TCP session. If you're curious, it's TCP port 179, but this is kind of like setting up a telnet, or more preferably a secure shell connection between your machine and a host. You get that TCP session set up, and then you exchange information over that session. That's what BGP is doing. It sets up a TCP session between two routers, and then, and I'll show you the messages that it specifically sends in a moment, but it's going to send messages back and forth, educating one another about what routes are available, which routes are no longer available, what errors do we have, what are our parameters. All that flows over a TCP session. And a little terminology shift for you from what you might be used to with OSPF or EIGRP. Normally, when we're talking about those interior gateway routing protocols, we say that they advertise network routes, and those routes are a network address and a subnet mask, or we might call it a prefix. It's the network and how many bits refer to the network and how many bits refer to the host. That's what BGP is doing, but it has a different name. It's called NLRI, and that's Network Layer Reachability Information, and it carries the address prefix and the length. The length is the number of bits representing the network. So it does do that. Why don't we call it just a network advertisement? Well, we can send some extra stuff. There's a lot of extra parameters we can also send as part of NLRI information. But I wanted you to understand that we just call route advertisements something different here. Honestly, I still call them route advertisements sometimes. But if you hear that acronym of NLRI, yeah, we're probably talking about a route advertisement there. And another huge difference between BGP and these traditional routing protocols is the way we select a route. With RIP, what is it? Hop count. Shortest number of routers that I have to transit through, that's the path I'm using. OSPF, it's a function of cost. You've got your reference bandwidth divided by the link speed, divide, you got your cost. Go with the lowest cost. With EIGRP, it's a bit more convoluted, but still, by default, it comes down to bandwidth and delay. And yes, there's a crazy formula, and you can do a lot of stuff with it. But basically, it's bandwidth and delay combined. But it's one metric, it's one value, and we say let's go with the lowest value, the lowest feasible distance, as we call it. BGP is very different. BGP does not just have one end-all, be-all metric that we're just going to go with the best metric. It has several different, they're called, for your notes, they're called PAs, path attributes. These different path attributes can be used in a sequential order. Well, we'll talk about the order in a moment, but they're going to be used in order to determine the best path. If the first one's called a weight, and we'll talk about what that means in a moment. But if the weights of two different paths are equal, then we'll go down to something called the local preference. And we keep evaluating these different path attributes until we find one that's not a tie. And oftentimes, we're pretty far down the list before we hit something that's not a tie. But we can manipulate those path attributes strategically to influence which path we take out to the internet. And equally important, people on the internet coming into our organization, which path they're going to take coming into our organization. Can we do that without going into the ISP's building and say, hey, can I reconfigure your routers for a minute? They're probably not going to like that. We're not going to be able to configure the ISP routers. We need to do all that influencing inbound and outbound on our router, and I'm going to do that for you live today. I think you'll really enjoy that one. And as far as categories of routing protocols go, RIP, we know, is distance vector, OSPF, ISIS. Those are link state routing protocols. I almost got into a discussion of EIGRP. I'm not going to do it. I disagree with a lot of the literature out there. Come see me in my EIGRP masterclass for that. I consider EIGRP to be a distance vector routing protocol. I'll not get into that argument right now. But BGP is a path vector routing protocol. Remember what a vector does, like in RIP? From your high school science or math class. What does a vector give you? It gives you two pieces of information: magnitude and direction. How far is it? And which way do we go, basically? Well, that's what BGP does. It's going to give us a variety of path attributes that tell us how far it is. And we're going to know our next hop address. That's where we go. But what is a path vector? Well, something that BGP gives us that nobody else gives us, no other routing protocol gives us, it actually tells us the entire path that we're going to be traveling. If I'm going from my network through ISP1, ISP2, ISP3 into some other network, It tells me, I can look at my BGP table and it shows me that I'm going through this autonomous system, then I'm going through this other autonomous system and this other autonomous system. And then finally I go into the autonomous system that holds the IP address that holds the IP address that we're trying to reach. And that's why we call it a path vector, because it actually shows you the entire path you have to go. Now, I want to go back and touch on something that's another big point of confusion. A lot of times people hear the term route reflector or confederation, and that kind of makes their head spin because we're not used to that with any other routing protocols. I just want to really simplify this for you, and I'll even set one of these solutions up. But there are two solutions to this issue. The issue is within an autonomous system, if I've got a bunch of routers and they're talking to one another and they're in the same autonomous system in the same organization, they're using iBGP. If they're using BGP, it's going to be iBGP, which we said was internal BGP. There's a rule, or I guess we could say it's an assumption. And that assumption is we have a full mesh of connectivity. In other words, every router in this autonomous system that's running BGP, it has formed a neighborship with every other router in this autonomous system running BGP. Kind of like I've drawn on screen. We've got autonomous system 65,000, and I've got 5 routers. And those red lines, that represents the neighborships. The reason this is necessary is by default, if one router learns information from a neighboring router in the same autonomous system, it's not going to advertise it out to anybody else, because it just assumes that whoever told it told everybody else, because it assumes this full mesh. The challenge is this just doesn't scale. Here I've only got 5 routers. Here's the math that tells us how many neighborships we have to have a full mesh of connectivity. We can use the formula n times n minus 1 divided by 2, where n represents the number of routers we have. Now in our case, we just had 5 routers, so 5 times 5 minus 1, 4, 5 times 4 is 20, divided by 2 is 10. Yeah, if you were to count those lines, there were 10 neighborships that we had to set up, and that was just with 5 routers. What if we do have this large enterprise and we're running IGP? I mean, at Disney, we had 500, we didn't run iBGP, we had 500 plus routers. Let's say we had just 10 routers. How many neighborships would we have to set up to have a full mesh of iBGP neighborships with 10 routers? Well, it's 10 times 10 minus 1 is 9, so 10 times 9 is 90, divided by 2. We'd have to have 45 neighborships. That's really going to eat into some processor cycles on our routers to maintain 45 neighborships. So we've got 2 solutions, as I mentioned. We've got confederations and we've got route reflectors. Here's the idea behind a confederation. We still have our overall autonomous system with the 5 routers that I showed you a moment ago. We still have autonomous system 65,000. But what we can do is go inside that existing autonomous system, and we can create a subset of an autonomous system. We'll call it a sub-autonomous system. And this sub-autonomous system is going, notice that sub-autonomous system 65,001 on screen, it contains 3 routers, and yes, they have to have a full mesh of connections. Every router, R2, R1, R4, they have to have a direct connection to each other, and they do. And then I created this other sub-autonomous system, 65,002, going between R3 and R5, and they're directly connected. But you see the beauty of this? Instead of everybody connecting to everybody else, I just have to have my sub-autonomous systems connect to any other sub-autonomous systems. So I've just got one link. That connection between R4 and R5, that is interconnecting my 2 sub-autonomous systems. So this gives us, using confederations, a full mesh of connectivity virtually. Now, by the way, these sub-autonomous systems, they're not going to be advertised to our neighbors outside of our autonomous system. This is just something going on within our autonomous system. But it's a pretty clever way to do it, I think. There's another way that I prefer even more, and I'll actually set this next one up for you in the live interface in a moment, and it's called a route reflector. You've got these same 5 routers in your autonomous system, and you just designate one of those routers, let's say it's R1, will designate R1 as a route reflector. And here's what a route reflector does. Let's see that it gets an advertisement in, an NLRI information from R2. Well, when it gets that, it just like a mirror, it's going to reflect that advertisement out to everybody else in that autonomous system that's using it as a route reflector. I think that's pretty elegant. We just point, there's like, it's kind of like a designated router. I never thought about that, but it's kind of like a designated router in OSPF, isn't it? You've got one keeper and reiterator of network information. That's what the reflector is doing. It gets the advertisement and it reflects it back out. And again, I'll set this up for you live in a few moments. But still on the theory, before we get into our first configuration, let's talk about how BGP neighbors are formed. When we form BGP neighbors, step 1, as I've already mentioned, is we have to set up a TCP session. And we're going to be communicating over that TCP session. So let's walk through the steps together. When we first have our routers configured for BGP and we bring up the interfaces, they're now connected. They are initially in the idle state. They've got a configuration, but nothing's happened yet. And since we set up that TCP session, that means we go through that 3-way handshake you learned about early in your network studies. Remember, if you and I want to set up a conversation, a TCP session with one another, I'll send you a synchronization message, an SYN. We call it a SYN message. And I'm asking, hey, can we talk? So step 1 of the 3-way handshake is me sending you a SYN saying, hey, do you want to talk? And if you want to talk to me, you'll acknowledge that with an ACK, an acknowledgement message. And if you want to talk to me, you'll send me a synchronization or a SYN message of your own saying, and do you want to talk to me? So I send you a SYN, part 1 of the 3-way handshake. You send me a SYN-ACK, part 2 of the handshake, and then I acknowledge the SYN that you sent me. That's part 3 of the 3-way handshake. So that's what happens next. We go through this 3-way handshake process, and we're in this connected state. And now these routers know about one another. The session is established and they are now in the active state. Don't be thrown by the word active. To me, active almost seems like, okay, we're golden, we're active. What active means is we're actively trying to form a neighborship. We still don't have a BGP neighbor. We've got a TCP session with it, but we haven't established a BGP neighborship with it yet. So one side is going to send an open, it's called an open sent message, saying, all right, we've got the TCP session set up. Let's open up this neighborship. And the other side responds with a confirm saying, yep, I got your open and I'm confirming that. Let's be neighbors. And then finally, at long last, we are in an established state. That's when we can start exchanging route information. So those are the different states and the messages that are exchanged as we're setting up that neighborship. There's a few other messages that might be sent once that neighborship is established. One is the open message that was used during the setup. What's in that open message? When I say, I want to open up a neighborship with you. What am I telling you? Well, I'm saying, here's the version of BGP that I'm running, probably version 4, and here's my autonomous system number. What's yours? It's like here's my phone number. What's yours? We exchange autonomous system numbers. There's going to be some timers that we'll talk about in just a few seconds, and I tell you what my timers are. I'll tell you my router ID, so you can recognize who I am, or you can use my router ID to represent me in our communication. And there could be some optional parameters as well. But let's talk about those timers. Once we get the session set up, there's going to be a keep alive timer. In fact, here are the default timers. There's a keep alive timer that I'm going to send to my neighbor every minute. Every 60 seconds, it's a keep alive saying, I'm still alive. 60 seconds later, I'm still alive. And as long as I'm the other neighbor and I keep getting those keep alive messages, I feel pretty good that my neighbor's still there. They're repeatedly telling me, they're checking in and saying, yeah, I'm still good. But, I mean, it's the network. Occasionally a packet's going to get dropped. What if one of those messages drops and it doesn't get retransmitted? Something happens. Do I say, uh-oh, they missed their check-in, I'm going to tear down that neighborship? No, we give them a little bit of grace. We say, well, let's give them some more time. We're going to wait for a second hello message, or I should say a second keep alive message. We'll say, all right, we'll wait a little bit longer. We wait 3 minutes by default, 180 seconds. And if I've still not heard from my neighbor in 180 seconds, something's up. I'm going to tear down that neighborship. And when we're exchanging that NL route information, basically, when we're exchanging route information, we're going to do that inside of an update message. And that's going to contain path attributes that we'll talk about later. If a route got added to the routing table, we'll send an update about that. If a route got removed from the routing table, we'll send an update about that. And from time to time, there's going to be some errors. And errors or any sort of notification, that's sent in a notification message. So over this BGP session, this neighborship, these are the messages that you might see if you were running something like Wireshark. And those would include things like the open message, keep alive, update, and notification messages. Now let's go out and do our very first configuration of the day, and there's going to be plenty of them. Our very first configuration, just to show you how easy it can be, here's our topology. I've only got 2 routers. They're in different autonomous systems. And all we want to do is set up a BGP neighborship between these 2 routers. R1 is going to advertise that network just above it, the 192.0.2.0/24 network. Router R2 is going to advertise the network just below it. And the routers should be able to see one another's networks. Pretty simple. And we're going to be able to do that by giving just 3 commands on each router. And then as we go through today, we'll get a little bit more involved in that. So I want to pull up a topology in my terminal window. So I'll make it a little bit bigger so you can see it. And the first thing we want to do here on router R1 is we want to go into router configuration mode for BGP. Very similar to what we would do with OSPF or EIGRP. I would say in global configuration mode, I would say router, BGP, and this is not just some process ID like we have with OSPF. This is my assigned autonomous system number. Looking at the topology on screen, very clearly we can see that R1, it's in autonomous system 64,500. So I'm going into router configuration mode for BGP autonomous system 65,400. And by the way, that was the first of 3 commands. I said it's only going to take 3 commands. Step 1 is go into router configuration mode. Now I need to say who my neighbor is. Remember, we're not going to be dynamically discovering neighbors. We're going to point to their IP address. I'm going to say my neighbor is, and I'll just use the ingress interface. We can do some other stuff and say I want to originate it from this source. I'm just going to keep it super simple here. I'm just going to go into the ingress interface of R2. That is 198.51.100.2. And then I have to say what autonomous system it's in. I'll say the remote AS, the remote autonomous system. For R2, we can see on screen it's 65,495. Actually, I did that. Did I do that backwards? Oh, no, I didn't. Yeah, it's in 64,495. I want to make sure I did not mistype that. That's step 2 of 3. And now I'm going to say what I want to advertise. I'm going to use the network command to say I want to advertise that network going up to SW1. It's 192.0.2.0. And I'm going to say mask to specify the subnet mask. And it's a 24-bit subnet mask. So I'll enter 255.255.255.0. Just double checking that I typed everything correctly. Checking my numbers. It's easy to mistype something. I think I'm good. Let me know if I'm not. And those are the 3 commands. That's all I have to do on R1. How simple was that? Let's go over to R2 and give basically a mirror configuration of that. I'll go into a BGP router configuration mode for 64,495 this time. And step 1 of 3. And I'll say my neighbor has an IP address of 198.51.100.1. It's in remote autonomous system 64,500. And I want to advertise oh, how quick was that? Notice that I just had a neighborship come up. I'm not advertising anything from R2 yet, but we just established our BGP adjacency. That's pretty awesome. Let's say network, because I want to advertise that bottom network going down to SW2. I'll say network 203.0.113.0, and I'm going to be using a mask of 255.255.255.0. We're done, folks. Let's see if we have learned about. Let's see if we've learned about routers or the routers on the far end and their networks. I'm going to say show IP route. First of all, have I learned about any routes via BGP? I have. I've learned about this route. Let me highlight it for you. I've learned about this route, which is the network going from SW1 to R1. I've learned about it via BGP. You see the B right there? The B tells me that I learned it via BGP. So that's working. Awesome. What about the other side? If I go back to... if I go to R1 and do a show IP route, can I see that bottom network between R2 and SW2? Yeah, I sure can. It's that bottom entry. And if I want to look at... the BGP table, see what networks it knows about, I can say show IP BGP. And it shows 2 networks that BGP has learned. And they are, I can highlight that, we've learned about the network that's locally connected to us, and we've learned about the network between R2 and SW2. Wow. How simple was that? Let me get back where my camera's on screen. There we go. And get back to our slides. I hope you would agree that it's pretty simple to do a basic BGP configuration. I mean, I've got 2 routers and 2 autonomous systems. They can advertise networks. They can form a neighborship. 3 commands. Pretty simple. Let's get a little bit deeper, though. Let's consider some extra stuff that gets a little bit beyond the basics. One of those discussions is path selection. Please be ready to take some notes here. For a lot of people, this is one of the most confusing parts of BGP. I don't want you to be confused here. Path selection is not as simple as it is with OSPF or EIGRP, where we just say, go with the lowest metric. Because we've got all these different path attributes. And depending on, it's crazy, depending on the literature you read, you may see that, oh, there are 11 attributes. Or some literature might say, no, there's a couple of extra ones. There's 13 path attributes. Yeah, there's a bunch, most of which we'll never use, by the way, or many of which we'll never use. So I want you to focus on what I consider the 8 primary path attributes, and I've got a memory aid for you that you might want to put in your notes. And that memory aid is, we love oranges, as oranges mean pure refreshment. If you can remember that, we love oranges as oranges mean pure refreshment, it's going to remind us of these 8 path attributes, which I would consider to be the most common path attributes. Wait, local preference, originate, AS path. I won't read them all right now, but let's discuss what each one of those mean. And a big point to remember as we go into this discussion, this is sequential. If I'm trying to compare different routes to go out to the internet, I've got 2 paths. I'm first going to look at weight. If one weight is higher than the other one, I'm going to go that way. And I'm not going to consider anything else. Doesn't matter if you've manipulated the multi-exit discriminator, you're never going to consider it because the weights are different. But if the weights are a tie, then we go down and we consider the local preference. If it's a tie, you get the idea. We sequentially go down through these. And let's talk about what each one of these mean right now. The first one is weight. And this is a Cisco proprietary path attribute, and we might use this when we're making an outbound path selection decision. So for example, I've got two ISPs, like we said earlier, and they're sending routes into me. Now, maybe I've got a gig link going to one ISP. I've got a 100 meg link going to another ISP. I want to use the one with the gig link. So how do I influence that? Because bandwidth is not, BGP doesn't care about bandwidth. It doesn't consider that at all in its calculation. But what I can do is, as I get these advertisements in, I can assign a weight of maybe 100 to route advertisements coming in over the slower link, and I might assign a weight of 200 for weight advertisements coming in over the faster link. And that path attribute is going to be applied to the routes being advertised. So when I'm saying, all right, which way should I go to this network? I'll go with the one with the highest weight. And that information, by the way, it's Cisco proprietary, and which is why a lot of people move away from that, because not everything is Cisco. And it's not advertised to any neighbors. Very similar to weight is the one that I personally prefer to use, and that's local preference. Local preference is also going to be used to make outbound path selection decisions. Higher is better. So I'm getting these route advertisements over my gig. I've got a 100 meg link and I got a gig link coming in. I want to assign a higher local preference value to my gig link to influence my traffic to go that way. Interestingly, this information, it's not Cisco proprietary, and this local preference that gets assigned to a route, it's carried throughout your autonomous system. Who knows? Depending on how things are hooked up, there's another router that might be able to benefit from that information too. So this is carried throughout the autonomous system, used to make outbound path selection decisions. And when I'm setting up a network like this, 9 times out of 9, I'm going to use local preference to influence outbound path selection. Now, next up, if everything is a tie at this point, we say that the first O, we love oranges. The first one is originate. Now, what that means is a lot of people get confused on this one, but for your notes, very simple. It simply means, am I connected to this network? If I'm connected to this network, I'm going to go out the interface that's connected to this network. I mean, I'm not going to consider any route advertisements. Basically, when you're looking at your BGP table, and I'll show you this in a few moments, when I'm looking at my BGP table, if the next hop is me, that means I'm connected to it, and I'm going to prefer that over something I'll learn from somebody else. That's what originate is all about. Now, we've talked about with weight and local preference, we've got these two ways to get out to the internet, and we're using those, or one of those, to influence which way we go out. But let's flip the tables. Let's say somebody is out on the internet, and they're wanting to come into our enterprise. If everything is equal up to this point, and usually it is from their perspective when they're trying to go to our network somewhere out on the internet, they're going to say, well, I've got these two ways of getting to Kevin's network. One way, I would have to go through 3 autonomous systems to get there. One way, I would have to go through 4 autonomous systems to get there. Remember, it's a path vector routing protocol. We see the path. We see how many autonomous systems we're going to have to go through to get to the destination. It's going to take a look at the length of the path. How many autonomous, it's kind of like hop count. Wow, can't believe I used a RIP reference. But it's kind of like that. We're counting how many or autonomous systems we have to go through in order to get to the destination. We're going to go with the shortest one. This is my go-to path attribute for influencing inbound path selection. So we've got these 100 meg link and a gig link again. I want people coming in over the gig link. But maybe because of let me give you a true story. When I used to work at a university, and we didn't have gig links back then, but when I worked at a university and we were doing this, we had one connection via AT&T. Now, granted, this was many years ago. We had one connection via AT&T that was a T1, a measly 1.544 megabits per second. And we got another connection from the state, that the state provided these connections to the different universities. It was 10 meg, which back in those days was a blazing fast internet connection. So I had 1.544 meg or 10 meg. I wanted to use the 10 meg. However, AT&T, being the big company that they are, they were a lot closer to the internet backbone than this state network that had to route through a bunch of colleges. It was much more attractive to people out on the internet trying to come into our university. In other words, the autonomous system path was much shorter. They didn't have to go through as many autonomous systems. So what do? And I'll demonstrate this for you live later today. We did something called autonomous system path prepending. Let's pretend that I don't remember what our autonomous system at the university was, but let's say it was 34,500. What I did is I prepended my autonomous system path that I advertised to AT&T. I said, yeah, to get to me, you need to go through autonomous system 34,500, and then you have to go through 34,500. Oh, and then you have to go through 34,500. You see what I did? I just gave multiple instances of my own autonomous system, making the path longer, so it became less attractive to people on the internet trying to come in, and that routed them through our faster link. So AS path is what I would normally use to influence inbound path selection from the internet. I'm normally going to use local preference to influence outbound path selection going out to the internet. But if things are still a tie at this point, we haven't manipulated anything, then we're going to see, how did this route get in the BGP table to start with? And this is not obvious when you're looking at even the help screen when you're doing show IP BGP and you see this little letter I. What does that even mean? Well, and I'll show you where this shows up in the table in a moment. When we're looking at the origin type, if it's an I, lowercase I, that means the way this route got into the BGP table was a network command. Just like I did a few moments ago in the live interface. I said network, gave the network address, mask, gave the mask. An I means it was entered via a network command somewhere. If it were an E, you'll never see an E. If it were an E, it means that it got into the routing table via EGP. I'm not generically talking about an exterior gateway protocol like BGP. No, I'm talking about that very, very, very old and now antiquated exterior gateway routing protocol that was called EGP. Yeah, I predict none of us will ever see an E in that position. Or if you see a question mark, which again I think is not very informative, that means the way that this route entry got into BGP was it was redistributed. That's a topic in the ENARSI studies, by the way, where you take one routing protocol like EIGRP and you redistribute it into BGP. Networks like that are going to get flagged with a question mark because they were injected into BGP from another routing protocol. Bottom line is, network command is preferred over an EGP protocol, which you'll never see, and that's preferred over something that was redistributed into BGP. If everything still is a tie, there is something that's called a metric in BGP, and it's called the multi-exit discriminator, or the MED. Up to now, higher has been better for things like weight and local preference. I said, yeah, the higher the numbers, you will use those. Here we're talking about the MED, the metric. Lower is better in this case. And what I can do is, I can stamp routes with a lower MED to prefer those routes. And I can advertise that to my neighbor. And when my neighbor wants to come back to me, if I have two connections, for example, to my neighbor, and I send them a MED for each connection, the one with the lowest MED, the lowest metric, they're going to use that one. But one more before we get to the one that I usually see. PAS. Remember we talked about iBGP that runs within an autonomous system that had a whopping administrative distance value of 200, and we said eBGP would run between autonomous systems. It had a very believable administrative distance of a 20. Basically, if you've got a network that's been advertised to you via both EGP and IGP, you're going to go with EGP. And if you don't touch anything, especially in a lab environment, this is what I see as the tiebreaker most of the time. It's the router ID. You can go in and statically assign a router ID, or you can let it pick one, and there's a whole process where it looks at the loopback interface IP address, and I won't go through all that now. But it's a best practice to just assign the router ID. In fact, I didn't do it in that simple demo, but I'll do it coming up. We're going to go with the one that has the lowest router ID. And if that's not the one we want, yeah, it's very simple to go in and change some of these other parameters. So we love oranges, as oranges mean pure refreshment. That memory is going to get you a long way. But even after you memorize that and you say show IP BGP and you're looking at a table like you see on screen here, where are the oranges and where are all those acronyms? Let me show you where they are. Let's go through it. We love oranges. The W in we reminds me of the W in wait, and it shows up in the output of this command. Notice that we have one wait that's really, really high. It's like 32,000 and something. The reason it's so high of a wait, notice the next hop is all zeros. That means we're directly connected to it. And that entitles us to have a very attractive wait. So there's where the wait is. We love oranges. The L is for local preference. Here, it looks like we've got local preference set to 100 for a couple of routes. And I'll set local preference up for you live in a bit. We also have our first oranges. We love oranges. This is saying the network is originating because it's connected to us. We're directly connected to this network because the next hop is 0.0.0.0. So that's going to be preferred over something we learn from somebody else, obviously. We love oranges as that's the autonomous system. And notice, for example, let me find one that has two routes. Actually, if we look at 198.51.100.4/30, one path has three autonomous systems: 65,002, 65,003, 65,004. Another way of getting there is to go just directly into 65,004. We're going to prefer that path to get to 198.51.100.4. How do we know that? Notice over here on the left-hand side, or excuse me, left-hand side, there is a greater than sign. There's a greater than sign right there. That means that is the preferred path. Oh, by the way, while we're here, you see the R right there? That means a RIB failure, a routing information-based failure. What a RIB failure is, BGP learned the route, but when BGP tried to stick this inside of the routing table of the router, it didn't take it. Is that a bad thing? Probably not. The router might have been directly connected to it. It learned it from a more believable source. So a RIB failure isn't usually a big deal, but that's what it stands for. But back to our acronym. We love oranges as oranges. The other O, that's the origin type. The origin type tells us how did this network get into the BGP table. And I means it came in via a network command. And that's preferred over an E, which you'll never see. And that's preferred over the question mark, which means it got in here because of redistribution. We love oranges as oranges mean. The mean, that's the multi-exit discriminator. I know it says metric. For your notes, metric equals med. Metric equals the multi-exit discriminator. Here, lower is better, and we haven't set any metrics, it looks like. We love oranges as oranges mean pure refreshment. The P is PAS. That's what that stands for. And it basically says, I prefer an eBGP path to an iBGP path. If it's an iBGP path, then there's going to be a little lowercase I like I've highlighted for you on screen. If it's an eBGP path, there's nothing. You only get flagged if it's an I. We love oranges as oranges mean pure refreshment. The R, that's the router ID. And you can see that up in the first line of the output. So those are the 8 path attributes that I would want you to memorize and understand and know where to find them. I think that's going to get you miles ahead of the approach, or at least it would for me, of trying to memorize like these 13 things with some of them have community attributes that are transitive and non-transitive. You'll probably never use that. These are the core path attributes that I really want you to know. Now, let's talk about this feature called BGP Synchronization that I hinted at earlier. BGP Synchronization is a rule that's been around for a long time. It was introduced, I'm trying to remember, I think this was introduced into Cisco iOS back in the 1990s, like early 1990s. It was iOS version 10 dot something. And the rule had a good intent. I'll give it that. The intent is, if I'm an autonomous system and I'm receiving a route advertisement from another autonomous system and I need to send that out to another autonomous system and I'm sitting here in the middle, when I get that route coming in from this autonomous system over here, before I will send it out to the next autonomous system, I need to make sure this is not going to lead to just a black hole, called black hole routing, where basically it doesn't exist. It's not going to go anywhere. And the check to make sure that this has some validity was, the rule says we're not going to advertise a network that we receive from another autonomous system. And one of my neighbors told me about that. My iBGP peer in my autonomous system told me about that network. I'm not going to advertise that out to anyone else unless that same network appears in my interior gateway routing protocol table, like OSPF. If I have OSPF running and it knows about network 10.1.1.0/24, and I'm trying to advertise 10.1.1.0/24 out to my eBGP peer, BGP synchronization says, all right, it shows up. You're going to be allowed to do it. There are plenty of times where it's fine if that network is not in an interior gateway protocol table. In fact, in some cases, you won't even be running an interior gateway protocol on some of these routers. They're just running iBGP. So most of the time, I want to turn this thing off. And that kind of became the consensus. And back in Cisco iOS 12.28t, which is, I want to say about, I'm guessing, I'm close. I don't know the exact date, but that's around 2002, I would think. Around 2001, 2002, over 2 decades ago, they just started making it turned off. There would be a command in BGP that said no synchronization. So since you're probably not going to deal with it today by default, why am I bringing it up? For the exam. You might need to know it for the exam. So let me give you a topology and we're going to go set it up. In this topology, I've got 2 autonomous systems. R3 has a loopback interface. And it has an IP address of 3.3.3.3/32. It's just a single IP address. And it's being advertised over to R2. That's its iBGP neighbor. Now the question is, if I receive something from my iBGP neighbor and I want to send it out to R1, that's in another autonomous system, so that's my eBGP neighbor. If I want to do that, can I? If BGP synchronization is turned on, the only way I'm going to be allowed to advertise 3.3.3.3 is if 3.3.3.3 also shows up in like OSPF's routing table or EIGRP's routing table. Now, if synchronization is turned off, I don't care what's in the routing table. I might not even be running an interior gateway routing protocol. I'll send that to my eBGP neighbor. So let's go out to the live interface right now and let's see what it looks like with and without BGP synchronization. We'll go back out to a live interface, and on, let's see, we'll begin over on R1, where this is where we're trying to see, are we receiving 3.3.3 or not? So let me go over to R1, making sure. Notice I got a bunch of routers that we're going to be on today. Oh, by the way, remember I said I estimated this was going to take about 2 hours? Yeah, forget I said that. Oh, we'll try to keep you updated on time as we go. But yeah, we got a lot of content today. But yeah, I am on R1, and let's do a show IP BGP. Can I see that 3.3.3? I forgot how many threes I said. Can I see that network? Yes, I can. Here it is. I can see that on R1. The reason is R3 advertised it to its iBGP peer of R2. R2 advertised it to its eBGP peer of R1, which is me, and I see it. Okay? Let's turn off synchronization on R2 and see the impact of that. On R2, let's go into router configuration mode for a BGP autonomous system. Let's see, 65,200. It looks, 65,200. And I'm simply going to say synchronization. That's it. Now I want to clear out my BGP table so it doesn't keep any old information. I'll do a clear IP BGP star to just clear those tables out and reestablish my neighbors. So we'll give it about 10 seconds to do that. All right, let's go back to R1 now. Do I still see 3.3.3.3? I don't. In fact, I don't see that network between R2 and R3 either. I don't see any. Oh, actually, I do see that one because that was not, R2 knew about that. It was not advertised to it. But 3.3.3.3 is missing. And the reason is I turned on synchronization. Now, how can I fix this? I know what you're saying, Kevin, turn off synchronization and that will fix it. Well, that's true. That is one way to fix it. But I want to make the point about what causes this in the first place. If I have a matching entry in an interior gateway routing protocol, even if synchronization is on, I'll still advertise the network. So let's go back to R2 and R3 and let's set up OSPF. We'll do it really quickly. I'll go into R2 and I'll say router OSPF 1. And here's my favorite network command. If I want all router interfaces to participate in the same OSPF autonomous system, I'm going to say network 0.0.0.0 with a wildcard mask of all 255s. And I'll say, which includes all interfaces, by the way. And I'll say, yeah, everybody belongs to area 0. So we'll do that on R2. Let's go over to R3 now. And I'll do the same thing. I'll say router OSPF process ID 1. By the way, those don't have to match on neighboring routers. And again, I'll say network 0.0.0.0 255.255.2 backspace 255.255 area 0. Let's give it a few moments for the neighborship to come up. We'll get a status message when that happens. I'm going to go over to R2 to stand by and wait for that. Let's do a show IP OSPF neighbors to see what state we're in. Yeah, we're in the X start state, so we're not fully formed yet. It'll be just a few more seconds. Still in the X start state. It's going to be worth it, trust me. By the way, I'm just taking a look at how many people we have joining us live right now. And it looks like on both platforms combined, we're pushing 900 right now. That's pretty cool. Okay, it says we have we've established a neighborship. So let's say show IP route. Has R2 learned about 3.3.3.3? Yes, it has. And that's okay. It knows about it because it learned about it from an iBGP peer. That's not what the synchronization rule is all about. The synchronization rule says, yeah, if I learn something from the iBGP peer, which I obviously just did, I'm not going to advertise it to my eBGP peer of R1 if the synchronization rule is on, and it is as well, and there's not a matching route in the routing table. Well, there is a matching route. OSPF has learned about 3.3.3.3. So now you could say that my interior gateway routing protocol of OSPF is now synchronized with my exterior gateway protocol of BGP So this should work. Let's go back to R1. 3.3.3.3 was not there previously. Is it now? It sure is. What a beautiful sight. Look at that. And I wanted to do that just to show you the behavior of the synchronization rule. Again, I doubt that you're going to be running into that in the real world, but for certification purposes, it's just one of those things I want you to know about. Let's get into BGP Deep Dive Part 2 right now, and we'll talk about BGP Summarization and Multihop. Now, summarization is something we see with some other routing protocols as well, but I think it is particularly beneficial in the BGP world. First of all, what is summarization? Just to make sure everybody understands what we're talking about. Here I've got 4 different networks, and I use some private IP addresses, but these are 4 networks. And if they all came into R1 and it wanted to advertise those out, it could do that as 4 separate advertisements. But there's something that these 4 networks have in common. They have a lot of bits in common. I'll show you mathematically in a moment what they are. The bottom line is, and I'll show you this, I'll prove it, I'll do a math proof for you here in a second, but all those 4 networks, they can be encompassed with a single route advertisement. And that single route advertisement is 192.168.0.0/22, which that could be what we advertise because they have the first 22 bits in common. Let me prove it to you. Here are those network addresses. And if you break each octet down into binary, you'll notice that, well, the first octet is the same. That's the first 8 bits. The next octet is the same. And in that third octet, the first 6 bits in that third octet are the same. So 8 plus 8 plus 6. We got 22 bits in common, folks. We've got 22 bits that all of these networks share. So instead of sending 4 individual advertisements, what if I did this? What if I took those 22 bits in common and said, I'm going to advertise a network with that mask. I'm going to use a 22-bit subnet mask. So I've got 22 network bits, 22 ones in my subnet mask, and then I've got 10 host bits, 10 zeros. If I convert those to decimal, I'm going to have a subnet mask that looks like 255.255.252.0. What's the network address? Well, we're going to bring down those 22 bits that everybody had in common. That's going to be the network address, followed by all zeros for the host bits. That's the definition of a network address. Here it is in binary. And if we put it in decimal, that's going to be 192.168.0.0 with a 22-bit subnet mask. So instead of advertising 4, and I realize 4 networks is not much. That was just to visualize it. We're going to take those 4 networks and summarize them as a single network advertisement. We're going to do that in this topology that we see on screen. We're going to go back out live and notice that router R1 has 4 loopback interfaces, and they're different IP addresses than the one in that example I just gave you, but if you look at them, they all also have the first 22 bits in common. I'm going to be able to summarize all 4 of those loopback interfaces with 10.1.0.0/22. So let's take a look at it before and after. We'll go to R3 and say, have I learned those loopback interfaces? Yep, 1, 2, 3, 4. I got all 4 entries. And then I'm going to show you how we can combine them into a single summary advertisement. Because if there's any place to do summarization, it's in BGP, because what did we have earlier? Over 900,000 routes in the complete internet routing table. I think there's some opportunity for summarization there. So I want to show you how to do that. And while we're out of this topology, I want to show you something else. Even though it's no big deal we said we had to have a full mesh of neighborships within an autonomous system. We call that iBGP. It works a little bit different with eBGP. With eBGP, by default, I can form a neighborship with my adjacent router, like R1 could form a neighborship with R2, but not with R3, because it's not adjacent to me. But with the eBGP multihop feature, I can get to a router and form a neighborship with that router that's potentially, it's potentially several hops away. So let's go out to the live interface right now and set that up. Let me pull up my correct topology. Got a bunch of topologies we're working with today. Let's go out to the live interface and let me move over to the correct router. Let's see. Let's start on router R3. Here we go. Here is router R3. Make sure I'm on the right one. No, that's not the right one. Let's see here. Here it is. All right, now we're on router R3 for this topology that you see on screen. And let's just take a look at the networks that BGP knows now. What's in the BGP table? I'll say show IP BGP. What we're specifically looking for are the loopback addresses on R1, and they're very prominent. Here they are: 10.1.0.0/24, 10.1.1.0/24, .2.0.3.0. It's these four networks right here. What we want to do to illustrate summarization is I want to show you in BGP how we can tell R1 to advertise a summarized address. For your notes, you might want to write down that BGP refers to that as an aggregate address. So to fix this, or to summarize this, let's go over to router, make sure I'm on the right router. Let's go over to router R1. I'll go into global configuration mode and into router configuration mode for BGP autonomous system 65,000. That's R1's autonomous system. And here's the command, if you want to jot it down. The command to do summarization in BGP is aggregate-address. And then I specify that summarized address. And I showed you the binary before. It's 10.1.0.0, and the subnet mask is going to be 255.255.252.0. That's a 22-bit subnet mask. Now, if I just pressed enter here, it would send a summary advertisement. R3 would see a summary advertisement. However, it would also see the individual networks. I want to hide that's kind of the purpose of this. I don't want to send the summary and then send all the individual networks. I want to send just the summary. So I'm going to say summary-only. All right, let's go over to R3. And do I still have all of those individual networks showing up? Great news, I don't. That aggregate address command made me see 10.1.0.0/22. That's the summarized address. But I could still get to any of those loopback interfaces because those addresses are encompassed in that single network. Now, let me show you something else. Let's do a show IP. Let's do a show IP BGP. And I want to, let's see. No, that's not what I wanted to do. Trying to think, did I already set this up and not tear it down for the demo? No, I didn't. 1 second here. Oh, I know what it was. I meant to say show IP BGP summary, my bad. Show IP BGP summary, that's it. I want to show you my neighbors. This is how we can see our BGP neighbors. And I've just got one neighbor right now. It's R2. And that's all I can have right now, unless I change the rule about forming an eBGP neighborship with a non-adjacent router, but that's what I want to show you how to do. Here on R3, let me show you how we can say, yeah, I want to form a neighborship with a router, but you know what? It's not adjacent to me. So here's what we can do. On R3, I'm going to say router, BGP, the autonomous system is 65,200. And for my I want to form a neighborship with R1. I'll use its ingress interface of 198.51.100.1. It's in a remote autonomous system of 65,000. Now, that by itself is not going to be sufficient. I'm going to have to say, I want to allow this to be more than just one hop away. I'm going to say eBGP could spell, that would be so useful right now. eBGP Multihop. And I'm going to say, I'll allow for 2 hops away. And I'm going to go do the very same thing on R1 to point back to R3. So let's go to R1. And I'll say router, BGP. Oh, no, that's right. Router BGP 65,000. 65,000 is what I meant to say. I'll point to R3 as my neighbor. I'll say my neighbor is 203.0.113.2, just double checking. And it's in a remote autonomous system of 65,200. And I want it to be multiple hops away. So I'll say eBGP multihop 2. And let's see if we have a neighborship come up between those 2 non-adjacent routers. Oh, look at that. We sure did. It says this BGP adjacency change happened. And if I do a show IP BGP summary, that's how I can see my neighbors. Yeah, look at this. Now I'm a neighbor not just with R2, I'm also a neighbor with R3. That is the eBGP multihop feature. Again, I emphasize that it's the eBGP multihop feature because we don't have that issue with iBGP. All right, let's get back to our discussion. And I want to take you back out to a demo where we're going to do some more advanced BGP configurations. First, let's talk about the topology, and this is I try to make this very, very real world. There are so many enterprises out there, like the university I was telling you about, that does peering with more than one ISP for redundancy, possibly, maybe for some extra throughput if we can set up some load balancing. But here's the topology I got for you. And in this topology, I know it's small. I'll try to make it a little bit larger when we go out to the demo so you can see the numbers better. But in the topology, see that big blue autonomous system, 65,001? That's what we're pretending is our enterprise. We're in that enterprise network with R1, R2, R3. R3 is our internet router connecting out to 2 different it's connecting out to 2 different ISPs. And then the ISPs, they connect into this other router that I've just named iNet for internet. And I created a loopback interface on that with an IP address of 5.5.5.5. So in this lab topology, what we're saying is if I can get to 5.5.5.5, then I've gotten to the quote unquote internet. That represents the internet. Now also notice the speed is different. The speed between R3 and ISP1 is 10 megabits per second. The speed between R3 and ISP2 is 100 megabits per second. So what do you think we're going to prefer? Yeah, I want to prefer to go to ISP2, but bandwidth does not factor into BGP's calculation, so we'll see what we're using by default, and who knows, we might have to change that default. So let's go out now to this interface, and I'll try to pull up the correct topology. There we go. Hopefully you can see those numbers a little bit better now. Let me get over to the correct router. Okay, we're on R3 in this topology. This is our internet router. And just for time's sake, I've already set up BGP on all the other routers. I just wanted to do a quick reminder of setting up BGP neighbors, and I'm going to do that here on R3. To do that, I'll go into global configuration mode, and I'll say router BGP, and I'll give its R3's autonomous system of 65,001. And I mentioned I would start using the router ID. That's the best practice. I'll say BGP space router ID is going to be 3.3.3.3. Now, a big point of confusion here. A lot of people see a configuration like this and they ask, am I advertising that I'm 3.3.3.3? If somebody, isn't that somebody's legitimate IP address out there in the world somewhere? Am I suddenly advertising that? No. Yes, it does look like an IP version 4 address, but it's just a name. It's a name that looks like an address. So don't be concerned that you're actually advertising 3.3.3.3. You're absolutely not. Let's point to some neighbors. I'm going to say I've got a neighbor of 10.1.1.2. That's R2. And even though it's in my same autonomous system, even though this is going to be an iBGP configuration, I'm going to say the remote AS is 65,001. Yes, that's mine as well, but we still say remote autonomous system, but that's going to be an iBGP peer for me. And I've got another neighbor with ISPs 1 and 2. Oh, notice I just had an adjacency with R2. That's good news. I'll say I've got a neighbor of 198.51.100.2, and that's ISP 1, by the way, and it's in a remote autonomous system of 65,000. Oh, it's 65,002. One more neighbor. It's going to be ISP 2. Neighbor 198.51.100.6. It's in a remote autonomous system of 65,004, it looks like. Oh, and you see that I had an adjacency come up with ISP 1. Great. Hopefully I'll have one come up with ISP 2 here in a few moments. And now I want to advertise a network. You see that network? Oh, and there's the adjacency that came up just then. The network between R2 and R3, that's the 10.1.1.0/24 network. Let's say that I want to advertise that out to the internet possibly. We'll pretend it's not a private IP address, but we'll say we want to advertise that out. I'll say network 10.1.1.0 with a mask of 255.255.255.0, and I'm done. Now, I know what you might be thinking. You might say, okay, Kevin, you advertised the network connected to R3 going to R2. You did not advertise the networks connected to R3 going to ISP 1 or ISP 2. Yeah, I omitted those intentionally. The reason I omitted those is I don't want to become a transit area. If I start advertising that I can get from ISP 1 to ISP 2, they might start using me to come through my enterprise when it has nothing to do with my enterprise traffic. Somebody could try to be going to Amazon.com and send their traffic through me. I don't want that. That's the reason I've chosen not to advertise those networks. Now let's verify the BGP configuration on R3 right now. Let's do a show IP BGP. Looks like I've learned about, I haven't checked, I'm just from first glance, I think I've learned about every single network in this topology. I've learned about this 5.5.5.0 network, which we said was a loopback on the iNet router. That's what we say is going to get us to the internet. Now, notice there are two ways of getting there. I could get there via 198.51.100.6 or 158 or 198.51.100.2. Two ways of getting there. Which way am I using? Remember, the greater than sign indicates my preferred route. I'm using 198.51.100.2 as my next hop. Look at the topology. That's ISP1. I'm using a 10 meg link to get out to the internet when I've got a 100 meg link available. What gives? Why is this happening? My weight is the same. My local preference is the same. Look at this though. The autonomous system path length is the same, but the router IDs on the routers themselves. Notice the router ID of ISP1 is 4.4.4.4. The router ID of ISP2 is 6.6.6.6. Because ISP1 had the lowest router ID, that's why it was selected, even though it is a suboptimal path. And that's just I so wish BGP would somehow consider bandwidth, but it does not. So we're going over a link speed that's 10 times slower as the other link. Okay, we'll fix that. We're going to fix that. So no worries there. But let's go to R3. Let's make sure that, or we're on R3. Let's make sure that R3 can get out to the internet. If I do a show IP BGP summary, I want to just make sure that I've got all my neighbors set up. Yeah, it looks like my neighbors are all established also. That's great. By the way, if I want to get really, really detailed information about a neighbor, instead of saying show IP BGP neighbors or just show IP BGP, I can say show IBGP neighbors, and it gives me much more information. Like for this neighbor, which is R2, it tells me its autonomous system number. It tells me this is an internal link. It tells me its router ID. Yeah, we're always, as far as I've ever seen, running BGP version 4. My state is established. All kinds of great information in here about our neighbors if we need that for troubleshooting. But the big question now is, can R3 get to the quote-unquote internet? Can it get to 5.5.5.5? Let's try. Can I ping 5.5.5.5? Yes, success. That's great news. R3 is getting there. I wonder if R2 can get there. Let's go over to R2 in this topology. On R2, let's take a look at the routes known to BGP. If I do a show IP BGP, wow, it seems to know about a lot of stuff as well. It knows about the 5 network. Awesome. But check this out. It knows about the 5.5.5.0/network or /24 network, but what if I try to ping 5.5.5.5? It fails. I need some troubleshooting help here, folks. Go ahead and chat it in. Why is this failing? R1 could get to 5.5.5.5. We have evidence that it advertised that network to R2. R2 has it in its table. By the way, R2 does not have it in its IP routing table, but it is in the BGP table. My question to you is why? Why can R2 not get to that network, even though it knows about that network? I'm taking a look at the chat interfaces. Any ideas? Ah, yes. Nicholas is the first one I saw with the correct answer. Great job, Nicholas. Nicholas says this parameter right there. Nicholas says the next hop attribute of 198.51.100.2, that's not reachable. If I look at my IP routing table up here, I have no clue how to get to the 198.51.100 network. So I'm not able to get to my next hop. If you take a look at where that is, that's the incoming interface on ISP1. R2 says it doesn't know how to get there. And it has to go there next, it says. So we got a problem. This is a characteristic of IBGP. This is why I wanted to make a big distinction early on today that IBGP and eBGP work quite differently. What's going on here is when R3 is advertising this network to R2, please hear me on this, please capture this in your notes. Because I'm sending this to an IBGP peer, it does not change the next hop attribute. That's the reason R2 cannot find its way out. There's a fix for that. We can set the next hop attribute. We can go in and we're going to do this. We're going to do this on R3. Let me go back to R3. And here's what I can do. Let's go back into router configuration mode for BGP 65001. And I'm going to say for the neighbor of R2, which is 10.1.1.2, I'm going to give this optional parameter. I'm going to say next hop self. I'm going to tell R2, hey, if you're trying to get to somewhere that I'm advertising to you, come to me. I'm your next hop. I'll end that. Let me quickly do a clear IPBGP. Let's reset everything. And then let's go back to R2 and see if its next hop is different. Hopefully it will be. Take a few seconds for this to complete. Looks like we've got some neighbor ships just now coming up. There's another one. Let's go back to R2. Is it seeing everything yet? Not yet. We'll give it just a few more seconds to learn everything. That's one of the things about BGP. It takes a while. By the way, there is such a thing as doing a soft reset with BGP and things come back faster. Personally, I've been working with BGP for like 25 years. And there are some things that get cleared out when you do a soft reset and some things that don't. I've never bothered to try to memorize what things do and what things don't. So I just always do a clear IPBGP. There we go. We're finally back. Now, for this 5.5.5.0 network, notice the next hop. The next hop is now reachable. The next hop is R3. So what do you think? Do you think I can now get to 5.5.5.5? Let's try. Ping 5.5.5.5. Success. So we fixed that with the next hop. Beautiful. Well, R3 is good. R2 is good. What about R1? Is it going to be good? Let's go check it out next. On R1, let's do a show IP BGP. Yikes, folks. This doesn't know about much at all. It only knows about 2 networks. What's going on here? Can somebody tell me why R1 has not learned these networks? I mean, R3 advertised them to R2. How come R2 didn't advertise them to R1? What do you think's going on here? Here's a hint. We talked about it earlier. Why did R1 not learn anything? I'm looking in the chat interface for both YouTube and our chat roll. Remember earlier when we were talking about iBGP and we said it had this assumption that there was a full mesh of neighborships? The reason it assumed that the reason it sort of required that full mesh of neighborships is if I learn something from an iBGP peer, I'm not going to advertise that to another iBGP peer because the assumption is that whoever told me told them. That's what's going on here. R1 is my iBGP peer. So I'm not going to tell anybody else in my autonomous system because I just assume R3 told that to me. I'm not going to tell it to R1 because I just assume R3 told R1 about it. And that's simply not the case. Now, what we could do, I could make R1 and R3 peers. I could do that full mesh thing that we talked about earlier. Or I could use one of the other 2 solutions that I gave you. I said we could use confederations. I think this network might be a little too small to really benefit from confederations, but we could alternately use a route reflector. I love that idea. Let's make R2 a route reflector. So I'm going to go to R2, and here's how you set up a route reflector. It is super easy, I promise. We're going to say router BGP. The autonomous system is 65,001. And for the neighbor of 172.16.1.1, I'm going to say it is a route reflector client. And I'm going to say that R1 is also a route reflector client. So if either router advertises something to R2, that advertisement, just like in that animation I showed you earlier, it's going to be reflected out to any other route reflector client. Now here's the cool thing about this. I don't have to configure anything on R1 or R2. I just have to go to the router that's acting as the route reflector and say, this is a client and this is a client. Now, did this fix it? Let's check it out. Let's go back to R1. And earlier, it had a pretty sparse BGP table. Now, if I do a show IP BGP, look at that. It knows about pretty much everything. Can I get to 5.5.5.5? Can I ping 5.5.5.5? Yes, I can. Awesome. So that is a look at setting up dual-homed BGP, going out to two different internet service providers. We saw a couple of issues with iBGP. We saw that we had to do the next hop self so that R2 inside the autonomous system could point to its peer, not to somebody out on the internet. And we also saw how a route reflector would help prevent us from having a full mesh of adjacencies. Now, while we're here, I want to talk about another concept. We'll just stay live in the interface, and let's talk about a peer group. A peer group is going to make our configuration hopefully a lot simpler. Let's say that we've got, now I know here we've got a fairly small topology, but if we had dozens and dozens of routers that were interconnected and they're all running BGP, if I started to apply a bunch of policies, or maybe I'm doing a bunch of route summarization commands, or maybe I'm filtering some routes, if I had to do that to every single router, that's a lot of configuration, and that could be a serious CPU impact. So what I could do, in many cases, what I can do is group a group of routers into a peer group. So then when I'm applying a policy or a summarization statement or a filter, I don't have to do it to this router and then go do it to this router and then go do it to this router. No, I do it to the peer group. And it applies to everybody in the peer group. Now, in this example, here's what we're going to do, just to illustrate this. In this example, let's say that R3, let me go back over to R3. Let's say that R3 wants to make sure that it's not receiving any network advertisements from its ISPs for private IP addresses. Now, those should not be transmitted over the internet. We just want to make sure they're not. Those RFC 1918 addresses. So what I could do is I could use a prefix list and I could apply it to ISP1 and say, I want to block any private IP addresses. I could then take that prefix list and apply it to ISP2 saying the same thing. Or I could put both ISP1 and ISP2 into a peer group and just apply the prefix list to that. Now, the point of today is not to teach prefix lists. That's another conversation. But just if you're curious, let me show it to you. I'll do a show IP prefix list. And basically what the first three lines are doing, these are denying those RFC 1918 addresses, and the bottom two lines are permitting everything else. Now, what I want to do is, instead of applying that to each of my peers, I want to create a peer group, and I want to apply that prefix list to the peer group, and then we'll make our two ISP routers members of that peer group. Here's how we do that on router R3. Let's go back into router configuration mode for BGP Autonomous System 65001. And I'm going to say I've got a neighbor called, we're going to say it's not an IP address, it's got a name of BGP-PG for BGP peer group. And I'm going to say it is a peer group. Awesome. Now I'm going to apply that prefix list right up here called BGP demo. I'm going to apply it to the new peer group that I just created called BGP/PG. To do that, I'll say for the neighbor of BGP PG, I want to apply this prefix list named BGP-demo, and I want to apply it in the inbound direction. So as I'm receiving network advertisements, I want to filter out those private IP addresses. Now I want to put my ISP routers in that peer group. To do that, I say, oh, you know that neighbor of 198.51.100.2, that's ISP1? I want them to belong to the peer group called BGP-PG for peer group. And I'll do the same thing for ISP2. I'll give its IP address. It is 198.51.100.6. So that's how, and again, I'm only doing this with two other routers. Imagine if we had 6 routers. That's a lot of configuration that we just saved ourselves because we applied these policies one time to a peer group. Now, I just applied one thing to the peer group. I could go apply other kinds of filters. I could apply other kinds of policies, route maps, all kinds of stuff could be applied to that peer group, but I don't have to do it on a neighbor by neighbor basis. I just apply it to the peer group, and everybody that belongs to the peer group, it gets applied to them. Now, once that I've done that, some of the other demos that we have coming up, they're not designed to work with these peer groups. So give me just a quick second here, and I'm going to get rid of this peer group. I'm going to say router BGP 65001, and I'm going to say no neighbor BGP PG, which was a peer group. Let's get rid of the peer group. And that got rid of my other neighbors. It got rid of ISP1 and ISP2 as my neighbors, so I need to put them back. I'll say I've got a neighbor of 198.51.100.2, and its remote autonomous system is 65,002. That's where ISP1 is. And my other neighbor, 198.51.100.6, it's in autonomous system 65,004. And hopefully that will come up in just a moment. I'm just trying to get back to the state we were before we set up those peer groups. Now, the next thing we want to do is fix a very, very real-world problem. It's like I told you about at the university, we had this issue where we had these 2 different link speeds, and going out, we were using the slowest link, and people coming in from the internet were using the slowest link. That's the challenge we have here. I showed you this earlier. On R3, if I do a show IP BGP, and I'm trying to get to the 5.5.5.0 network, notice I've got 2 ways of getting there. The preferred way is indicated with the greater than sign. If you look at the topology, that's ISP1. That's the 10 meg link. I'd rather use the 100 meg link. Let's go out to our internet router and see how things look coming back in. On the internet router, I'm going to say show IP BGP, show IP space BGP. And let's say that I'm trying to take a look at that network that was advertised from within my enterprise, the 10.1.1 network. Here it is. There are 2 ways of getting there. 203.0.113.6 and 203.113.1. And it's preferring .1. And I'm just looking really close at the topology to see which one that is. Bad news, folks. It's ISP1. So we're going out over the slow link and we're coming back in over the slow link. Well, let's fix that. Remember when we were going through those path attributes, I told you a couple of different ways that we might fix that. I said to influence outbound path selection, I'd like to use the local preference. To influence inbound path selection, I might do autonomous system prepending. So, and remember, there's different ways of doing this, admittedly. We could use weight, we could use metric, but here's a criterion we have. We're not allowed to touch the ISP routers. That belongs to them. They're not going to let us walk into their data center and start setting stuff up. So what I need to do is I need to do all my configuration on R3. We'll pretend we don't have the right to do anything in the ISP cloud. So on R3, can I control inbound and outbound? I think I can. I'm going to do it. First of all, let's create a route map. You learn more about route maps in our ENCOR class, by the way. We'll say route-map, and I'm going to call it local pref for ISP1. Just so it's I can look at that name and know what it is. I want to set the local preference for routes coming in from ISP1. Remember, higher is better. So I'm going to give ISP2 a higher local preference. I'll say set local preference 100. which I think is the default. I probably could have left that alone. But just for thoroughness sake, I'll say the local preference is 100. Let's create another route map. I'll call this one local pref ISP 2. And for this one, this is the one I want to use. I want to go out over the 100 meg link. So I'm going to make this more attractive. I'll say set local-preference 200. So now I've got these route maps. I simply need to apply them to those neighbors. So let's go into router configuration mode for BGP 65001. And I'm going to say for my neighbor of 198.51.100.2, which is ISP1, my slow link, I'm going to apply the route map that I just created named local pref -ISP1. And I want to do this in the inbound direction. So when I visualize this, as ISP1 is sending frames into the router, it's like I'm taking a rubber stamp and I'm rubber stamping all of these networks coming in with a local preference of 100. For all the networks coming in from ISP2, I want to rubber stamp them with a local preference of 200. To do that, I'll say for my neighbor, just up arrow, for my neighbor of 198.51.100.6, I want to apply the route map local pref -ISP2. So routes coming in from ISP2, I'm going to stamp them with a value of 200, and that's going to be preferable, I think. Now, while we're here, we'll check it all in a moment. I think I've fixed my outbound path selection, but what about inbound path selection? Right now, because of router ID, the internet is sending traffic through ISP1. Let's make that route look less attractive, and I can do that by exaggerating my autonomous system path. Here's how I can do that. Let's create another route map. I'll say route-map AS path. That's not a keyword, that's just the name I'm giving it, so I know what it is. And I'll say set the autonomous system path to prepend a few values. Now, I'm in 65,001, but just instead of saying, yeah, if you want to get to me, come into 65,001, I'm going to exaggerate that by saying, yeah, first go into 65,001, then go into 65,001, and then you can come into my 65,001. You see what I've done? I've exaggerated the number of autonomous system hops that we have to make. Now let's go apply that to ISP1. I'll say router BGP 65,001. My neighbor is ISP1 198.51.100.2. I want to apply the route map called AS path, and this time I'm going to apply it in the outbound direction because I want to send that exaggerated autonomous system path to ISP1. So it's not going to look as attractive as it did with as it did earlier. And let me just reset all these connections real quick. I'll say let me back out, and I'll do a clear IP BGP star. Let's let everything reset, and we'll see if we fixed our issue. We'll see if it's now going to use ISP2 to go out and ISP2 to come back in. I hope it does. Looks like our neighbors are being reestablished. We'll give it a few more seconds to relearn everything on R3. Let's do a show IP BGP. Looks like we've learned about everything. Let's take a look at how we're going to be getting to I don't see my greater than signs yet. I don't think it's quite finished. Yeah, it should be telling me the preferred route with the greater than sign, and it is not. Let's take a look at our routing table. Show IP route. This tells me how I'm going to get there. This tells me my preferred path. To get to 5.5.5.0, I'm going to go to 198.51.100.6. And if you look at the topology, awesome news, that's ISP2. So we've now influenced our outbound path from ISP1 running at 10 meg to ISP2 running at 100 meg. And yeah, I just didn't wait long enough earlier. We see it confirmed now. There's the greater than sign, and we're pointing to ISP1, our faster link. Not what we had before though. So we fixed outbound path selection. Let's see what the status is of our inbound path selection. Before, when I did show IP BGP, to get to this 10.1.1.0 network, the preferred path was 203.0.113.1. That was ISP1. Hopefully this time it's going to be .6. Let's do a show IP BGP. Now the preferred path is .6. Awesome. That's ISP2. Why is that? Look at the shorter autonomous system path length for ISP1 as compared to this massive autonomous system path with this was with ISP1. Yeah, we're preferring ISP2 with the short path. Look at that. Yeah, what we did, we pre-pinned a couple of instances of our own autonomous system. So now we have successfully influenced inbound path selection and outbound path selection. And I'm just going to stay live here in the interface as I want to show you another way of setting up BGP, and specifically, this is going to be that multi-protocol BGP that we talked about earlier. Let's go back to R3 to do this. And I want to bring up a different topology because we're going to introduce IP version 6 now. Here is the same topology. In fact, let me make it a little bit bigger for you. I don't think that's going to block any of our text on screen. There it is. That's a little bit bigger for you. And notice that we now have the same addressing we had before, except between R3 and ISP2, I've added some IPv6 addressing. I didn't want to take the time to go set up IPv6 everywhere. I just wanted to show you how you could set up IPv6 using multi-protocol BGP. And the way we're going to do this is using something called address families. We're going to have an address family for IP version 4 and an address family for IP version 6. Now let's do some quick work to add IPv6 addressing to R3 and to ISP2. Again, that's the only link where we're going to be setting up IPv6. So in R3, let me just quickly add some IP addressing. Oh, by the way, here's something if you've not worked with IPv6 that's not at all obvious. We have to turn on routing for IPv6 or it's not going to work. I have to explicitly say IPv6 unicast routing. Otherwise, we're not going to be able to route IPv6. Now, I'm going to go into interface loopback 0, or excuse me, let's go into loopback 1. In interface loopback 1, I'm going to give it an IPv6 address of 20.0.1:1/64. That's its IPv6 address. Let's now assign an IPv6 address to the link going out to ISP1. That's gig 0/3. So I'll go into interface gig 0/3, and I'll give it an IP address. I'll say IPv6 address 20.0.2:1/64. Okay, I think we're done here. Oh, let's do one other thing. Let's get rid of our previous BGP router configuration. I'm going to get rid of that process. I'll say no router BGP 65001 because I want to show you how we can set this up using address families. So I basically just turned off BGP on R3. Now let's go to the other end of this, ISP2, and set up sort of a mirror configuration. I'll say allow IP version 6 unicast routing. That's supported now. Let's create interface loopback 1. Let's give it an IPv6 address of 2000:3:1/64. Let's go into the interface connecting up to R3. We'll say interface gig 0/1. Oh, I gave interface twice. Let's give it an IPv6 address of 2000:2:2/64. Notice that it's on the same network as R3, that they share that same link. And I'll get rid of its router process. I'll say no router BGP 65,004. Okay, this is our beginning spot now. Again, I'm not going to set up IPv6 everywhere just to demonstrate how it's done and how address families work. I'm going to set it up just between R3 and ISP2. R3 and ISP2, they each have a loopback interface, so they should, at the end of this, they should be able to see one another's loopback interfaces. Now first, and this is not obvious, first I need to create a route map that's going to advertise our egress IPv6 address as the next hop. So when R3 sends an advertisement to ISP2, I have to say, oh, by the way, I'm your next, kind of like the next hop self, I'm going to say, I'm your next hop. Now we begin doing this just by creating a route map. Well, actually, I want to be on R3 for this. Let's go back to R3. And on R3, I'll say route-map. And I'll create one called IPv6-next-hop. And I'm going to make myself the next hop for any advertisement that I send to ISP2. I'll say set IPv6 next-hop and me 2000:2:1. That's my address. Next, we began configuring multi-protocol BGP, much like we did before, to support the routing of IP version 4. Actually, we're going to set up routing a couple of different ways. We're going to create an address family for IP version 4 and one for IP version 6. But first, I'm going to just do what we did before. I'll say router BGP, and I'll give my autonomous system number of 65,001. So I want to point to a neighbor. I'll point to my neighbor of ISP2. It's 198.51.100.6. It's in a remote autonomous system of 65,004. So far, no difference. You'd say, okay, what's different about this, Kevin? You just deleted all this. Here's where it's different. This is multi-protocol BGP. And the multiple protocols that I'm supporting are IP version 4 and IP version 6. So I now create an address family for IP version 4. And I'm going to say what IP version 4 network I want to advertise. I want to advertise 10.1.1.0 with a 24-bit subnet mask of 255.255.255.0. Let's do the same thing for address family IP version 6. And I want to advertise the IP version 6 network of 2000:1:/64. Not an IP address, but a network. That's my loopback. That's the address, or that's the network to which my loopback interface belongs. And when we configure the IP version 4 address family, our specified neighbor that I gave, it's going to automatically be activated. However, here's what's not obvious. We have to manually activate the IP. We have to manually activate that neighbor for the IPv6 address family. And also, we want to associate our previous configured route map with this so that we know that we're advertising ourselves as the next hop. So again, I don't need to do this for IP version 4, But for IP version 6, I need to activate my neighbor. I'm going to say neighbor 198.51.100.6 activate. Now I want to apply the route map to say when I'm sending an IPv6 route advertisement, I'm your next hop. Neighbor 198.51.100.6. I'll apply the route map of IPv6 hyphen next hyphen hop. Oh, and I need to do that in the outbound direction as I'm sending advertisements out. Now I'm going to go over to ISP2, the other end of this link, and give just a mirror configuration. So I'll do this one quicker because we're doing the same thing just in reverse. I'll say let's create a route map called IPv6 next hyphen hop. Typo there. IPv6 next hop. I'm going to set myself, ISP2, as the next hop for advertisements going out to ISP1. Set IPv6, next hop, me, 2000:2:2. Now, let's create our routing process, router, BGP, Autonomous System 65004. My neighbor is going to be 198.51.100.5. That's R3. It lives in a remote autonomous system of 65,001. And now comes the address families. I'm going to say address family for IP version 4. I want to advertise the network of 203.0.113.4. With a 30-bit subnet mask of 255.255.255.252. Oh, and we saw an adjacency come up. That's good news. Let's do address family for IP version 6. We'll say address family IPv6. I want to advertise my loopback interface, which is 2000:3:/64 is its network. Remember, I've got to activate my neighbor for IPv6. It doesn't happen automatically. So for the neighbor of 198.51.100.5, R3, activate. And for that same neighbor, I want to apply the route map that says I'm your next hop when I send it an advertisement. I'll say route hyphen map, IPv6 hyphen next hyphen hop, and I'll apply that in the outbound direction. Now let's do some verification for both IP version 4 and for IP version 6 networks. You see this one command structure, this multi-protocol BGP, it let me set up everything, IPv4 and IPv6. So for ISP1, what's my routing table look like? If I do a show IP route, I see my IP version 4 networks, or I'll see the one because we got rid of the other configuration. I see an IPv4 network that I learned via BGP. If I do a show IPv6 route, have I learned about the loopback interface on R3? Yes, I have. It's that top entry right there. That's R3's loopback interface. Awesome. And if I do a show IP BGP, yep, we see that I know about those two networks, and I think that confirms everything. I think we now know, just to summarize that somewhat lengthy demonstration, I think we now know that in this topology, we could set up IPv4 just like we did at the very beginning of class today, where we said those three commands: start the process, router BGP autonomous system number. Step number 2, point to your neighbor and its remote autonomous system. Step number 3 of 3, what network do you want to advertise? That was it. We could do that for a large topology like this. We saw in this demonstration also how we could influence inbound path selection by prepending a bunch of autonomous systems to our neighbors as we advertise those. And we can influence inbound path selection by rubber stamping these local preference values on routes being advertised into us. The higher the local preference, the better. And we created route maps to do that rubber stamping. And then we saw how we could use multi-protocol BGP and basically do everything in one structure, which is a beautiful thing. We can do this with EIGRP, with OSPF, with BGP. They can all use address families these days. So that is, hopefully that was a bit more advanced for those of you that knew the basics earlier. And I promised at the very beginning of class today, I said, you know what, if you'll stick around to the end, I want to give you a PDF of today's slides. I want to give you the .yaml files for all the topologies that we use today, so you can put that in Cisco Modeling Labs if you want to do it on your own. And I want to give you a PDF containing the base configurations that you can copy and paste into those topologies, and the step-by-step instructions that we went through in today's demonstration. So there is pretty much every demo we did today. Using those resources, you'll be able to reconstruct that on your own. To get it, totally free, just go to kwtrain.com/BGP-download. Again, that's kwtrain.com/BGP-download.